Today I'll say a few words about the CoolTower. It's a project that I'm busy in the last 4 years actually. I'll start with a small introduction about myself and about also Rossum, and then I will go on with different parts of the CoolTower, like the foundation, the plinth, and the tower itself, and then we go to the Q&A. So my name also says I'm come from Greece. I did my studies first in Greece, bachelor and master in civil engineering, and then after working for a year in Greece and also going in the army, I came in Netherlands and I did my master in TU Delft and in building engineering and civil engineering. So, and since the 2014, I work at Rossum. It's the first company I work here. It's still it's remained the same, and my role is now project leader and structural engineer. And so, which means that actually this was a role also when I started, and it's really important to know that when we work at Rossum, everybody has starts and can also take a small project and can also become a project leader from the day one. Then we have 4 offices in total. We are around 170 people. I see now, when I started in Rotterdam, we were with 10 people, and now we are 40. So we are growing and growing and growing. And you see, we also need more people, also interns or graduates, or even more junior engineers to start working, because we do have a lot of work for you guys. The company exists many years, since 1953. The main goal of the company is to create relationship with the clients and satisfy their needs, their dreams. And we do that by working together with the client, having really close contact from the beginning of the project till the end. So we are actually the advisors of the client instead of just doing the small engineering. And the clients trust us for that, and that's why we do have also many and very interesting projects. We are very open in the communication also with the clients, but also inside the company. You can communicate from the top manager to anyone without any issue. For me also a bit different, because I come from a country where the leadership is very important and really respectful. And here I saw that this is not an issue, and I was very happy with that. Then we do have in the company, we can do trainings, but also a lot of knowledge to improve and get better in any field you would like in the engineering. We are, as engineers, I would say that we are doing the full package of the structural engineering. So we do the design, but also we advise during the construction, we advise during the start, and we work together with the architect, together with the client, but also together with all the different subcontractors to achieve the most optimum and the optimum in design, but also in cost and efficiency project. If you want to know more, you can go in our website, and then you can see everything that you would need. And you can always contact people from the company. My experience. As I said, I come from Greece, so when I started working in the company, I started in English. Now I got the full support from the company on that, and I do everything in Dutch. We always have young colleagues that you can always do external activities. You can do bottle drinks. We also have, but we also have experienced colleagues where we can always ask questions, and you can always learn from that. You can always anything you can in mind, you can ask it, and there will be someone to help you with that. What I find very interesting by Rossum is that from the day one, you can start from the most simple thing by calculating a beam, or even by archiving some drawings, And then the other day you can work and make a very complicated tower in 3D and make calculations on that. And this variety of responsibilities is very important because you learn a lot in very few time. You have the opportunity to work in many different projects. So for me, for example, when I started working Ponsteiger, I made there the load and stability calculation of the lower part, which was for me very, very impressive at that moment, and still is. Then I also worked on a school like Retail Academy. It was an expansion, but also in a villa of 250 years old where we did the whole restoration. So you see there are many different projects you can work on and many different skills you can acquire from that and knowledge. My work in Rotterdam. So I think last time my colleague Floor gave an analysis, a small presentation of the projects in Amsterdam. These are the projects now we're having in Rotterdam. These are actually projects that I worked on and I'm working now. And today we're going to talk about project number 13. It's the CoolTower. And you see that the varieties here also a lot because they are from office buildings to apartments to malls. It can be anything. And we are still expanding and still getting new projects for new work. And now the CoolTower. The CoolTower is as you can see, has a very interesting silhouette in the sky of Rotterdam. And there are different buildings that now are being built in Rotterdam, and this is standing out because the form of the facade and the form of the building is different. You can also see that the facade starts from the top and from the lower part as a light and thick element and thin elements, ends up in the middle with thick elements. And this was actually the goal of the architect, because the architect wanted to achieve this one. This is the first drawing of the architect, which you can see that it's very dense in the middle. And the idea of that is that all the average height of the high-rise buildings in Rotterdam are around 75 meters. And this is the middle part. So he created there a sort of point to see, to have an a location for all the average height. And this is actually being built, and he achieves that through the thickness of the balconies. It is located in the area Cool in Rotterdam. That's why also the CoolTower, besides being a cool project. And it's between the streets Baan and Hoornbrekenstraat, and you can see actually that it's above Hoornbrekenstraat. So there was a need to create a sort of construction, which we're going to talk very soon, to transfer the loads above the street. The area is now being really developed, and there will be many different developments in this same area. You already know that we're going to make also the Baantoren. It's next to the CoolTower, and it's going to change completely compared to what it was. The project parties, the architects were the architects. We worked a lot together during all phases. It was a very smooth collaboration. They understood the needs of the building, because in this project it's very interesting that the structure is prevailing in relation to the architecture design, and they accepted most of our requirements in order to make the building safe and stable. The client is the 5 here in BV. We're doing a lot of projects with them. Contractor is a very big, famous Dutch contractor. It's Ballas Nedam. And as far Rossum, we have in every phase, we always work with one project leader, one structure engineer, and one draftsman modeler. But these people change in every phase. So 4 years ago, when I started with the project, I was doing the calculations, and now I'm doing the project leading during the construction phase. Some data of the project: it is a residential building. It is made out of concrete and steel. mainly from concrete, but there are also some steel elements that are main structure. Total height is 155, well, approximately 155 meters. And you see that the completion date is mid 2022, and now they are almost in the middle of the project of the construction. So they have a lot to do yet. These are the main elements of the project. I divide it in three main parts: the foundation, the plinth, and the tower. And you can see on the right picture that the plinth is separated also in the wings. And I call them the wings because those two parts are actually hanging from the tower and they are not supported to the ground. They are cantilevering from the tower, and they are supported on the big foundation plate. We will see more about that in the next slides. And the tower is divided on the main characteristics of the tower are the outrigger walls, which are part of the stability system. And and from the plinth, also at the left side, you see the transfer structure, what I was talking about, that it goes above the homebreaker strut, and it's necessary in order to create a clear path for the cars and to go through. The foundation, you see on the top, the form of the plate is a bit weird to have like that, but it was necessary because at the location of the homebreaker strut, there are a lot of cables and a lot of installations that we couldn't remove them. They had to go on during the construction, so we had to create the pour in this way, and that's why we made this form of the foundation plate, which is 2 meters thick. Then you see on the lower part all the piles, which are placed in the whole foundation. There are in total 167 piles. Most of them are in the middle part, in the foundation plate, and there are 3 left and right at the wings, which are the parts that they are cantilevering from the tower. This is a drawing we made. We call it the form drawing. We made for the last phase of the project. So based on that, the contractor will make his own design and his own planning, and he will actually construct the foundation. And here you see a photo of while they are pouring the concrete of the foundation plate. You see all the reinforcement and the amount of concrete that is going continuously in the foundation plate. Also here you see the sprung, the lip in the foundation plate. Some facts: the concrete foundation is 2 meters thick and it's 31 by 31 meters. In total, 167 piles, as we said. It has a pile length of 55 meters, which is almost 1/3 of the building is also in the ground. You see here the analogy in the height. And the load capacity of every pile is approximately 8,000 kilonewton. I don't know, probably my colleagues already know that, but I don't know about the students if they understand the amount of this massa that comes, or this kilo that comes on a pile. But I made a small analogy, and you can see here that a fully weighted, a fully loaded Boeing is around 300,000 kilos. So a pile can have approximately 2.7 Boeings if it's possible to support on them. So you see, every pile takes incredible amount of loads. We move at the plinth. The goal of the architect was to create a facade where you could see that you see on the left side and the right side is different, and the idea was he wanted to keep the same form from the previous construction, and he actually achieved it making that. There are 2 main floor plans in the plinth. The one where the homebreaker strut goes through, so you only have a part the plinth, and then from the 3rd to the 7th floor, the tower is going above the homebreaker start, and then it also becomes also functional use, this one. Here's what I was telling before. So we have on the left and the right, we have the wings of the plinth, and through the cantilever walls, which are the green ones, they are connected with rebars through the walls, through the floors, and also through the walls, and they are hanging from each other. So they are holding themselves in place, so they will not collapse. And then here, the yellow ones is the transfer construction, which is transferring the load from the tower above the homebreaker start. It's the transfer construction is 5 trusses and 2 walls. We will see more about that later. Here, a section of the situation. You see that on the left hand side, the cantilever walls, and here they are supported on that part and on that part, and through the tension reinforcement, they are keeping themselves in place. So, and the idea of that was because we didn't want to have a difference in the deformation between the tower and the plinth, because the tower is 50 meters tall and the plinth is only 7 meters. It's only 21 meters tall. So the tower is 50 floors and the plinth is 7 floors. So there will be difference in the deformation, and also we didn't want to affect the buildings next to the plinth, and that was the solution we found out, and it solved this issue. This is the transfer construction, what we discussed before. So you see there are trusses that they come above the street, and they take all the loads from the columns and they bring it left and right to thick walls, so that we can have an access through the street. The main idea of the structure is that it takes on the left side, it takes the loads from the columns and it transfers it to the walls. This is how it works in the normal situation. But we also made the research, and it's necessary in this kind of buildings, how the trusses will function if one part collapses. And so in this specific case, if this beam collapses, we see that how it's going to transfer the forces to the tower from on the top here and on the bottom, and then we had to reinforce and we had to calculate the elements based on these forces. So we also have to think about these scenarios during our work, not only about just making calculation of the normal situation, but also what happens in case of accident, what happens in case of during construction phase. All these kind of parameters, we take them in account. One nice part of our work is that we can see it in a design, we can design it ourselves, and we can see it being built. So it's although it's what I find very pleasant and very satisfying when you have worked really hard and you have really enjoyed, and you can see this being built and you enjoy it. Now the tower, this is what it's going to be, and this is what's happening now. You see it being built now. The picture is not so good, but now they are still building that, and you see the form how it's going to build. The stability system of the tower, it is actually the buildings are stabilized through the core walls, but in this case, because the core walls were not stiff enough for the loads, we decided to create 2 outriggers. So it's here on the 16th to the 20th floor, and on the 32nd to the 36th floor, in order to create extra stiffness to the construction and to make it to realize the way the architect and the client wanted. The idea is that there are four floors of walls in every outrigger that they transfer the forces, and then we use also the prefab columns for this construction. This is a typical floor plan of the tower. This is it. It doesn't change well in all floors. in terms of dimensions, but then there are differences in terms of the balconies, in terms of the stability system, and in terms of the structure system, which I'm going to go through now. From the 8th to the 50th floor and the 21st floor, we have the same construction. The red ones are only transferring vertical loads, so they are not part of the stability system. And then the blue ones and the green ones also transfer vertical loads, but they are also part of the stability system. So we had to make this kind of separation in our calculation. The prefab balcony, the balconies are prefab. They are 2.4 meters, and the floor is 250 millimeters thick. As we go higher, you see in the tower, you see this is the levels with the outriggers. So here, the yellow ones are the outrigger walls that are being used for the stability system. And then we reached the middle part where we have the mid crown, that's how we call it, and above and lower the mid crown, there are also a different floor plan where the balconies become steel because of the length of balconies. So that it wasn't possible to make it in concrete, so we decided to make it in steel. And the rest of the construction remains the same. And then here we come to the middle crown, which was the main idea of the architect, to create this kind of ring around the building, so everybody can see it around this dense line in the middle of the construction. Again, here, because of the length of the balconies, we had to make them 3.2 meters. We had to make them from steel. And the difference is that in these floors, we had to add these extra beams on the edge of the balcony of the floors in order to support the balconies. But further, the construction remains the same, like the floors below we discussed. So here you see the idea of the architect is from the architect, and here's how this is going to be made, the steel construction. Later there will be around concrete elements that will cover, of course, the steel. One, is not going to be visible, and you're gonna see that one. Above the outriggers, all the columns are not anymore stability elements, and that's why you see that they also become much smaller. They also don't take so much loads compared to the lower ones, so the dimensions are getting smaller, and that's also good for the contractor and the client, because we also think about that. We have to think and how to make it smaller and more efficient. That's the idea behind this. And you see that from the start, although the form remains the same, you have many varieties and many differences in the construction. On top of the house, of the tower, we have the penthouses, and here the form changed completely. It becomes more. It's less, but the structure is and also the structure changes, because the columns are not taking any stability loads, but only the walls, the prefab walls in the middle, are taking the stability loads. And these are actually, in my opinion, they're going to be the most beautiful apartments or penthouses in Rotterdam. If you see the designs inside from the architect, it's going to be very impressive. So since we made the design, and since we made all the elements, and we know what we're going to do, we use SIA models to calculate the forces, and of course control our options and see if what we designed and decided are correct. And we have two main models in SIA. One is without the influence of the ground, and the second one is with the influence of the ground. The reason we make this separation is because we want to see what's going to happen on the ground because of the formation of the ground after 50 or 60 years. Because as you know, the ground in the Netherlands is a bit weak, so we need to take this in account in order to design our structure. And then on the first model, we made 3 different separations in order to check the different elements and different situations. So in the first one, we We assumed that the columns, they have the same stiffness with the core walls. We made another model where the columns are stiffer. Are stiffer than the core walls, and another one where the columns are the same with the core walls, but the floor is 10 times lower the stiffness. All these are happening because we can't calculate with one model all the different situations, and you need to check what's the most important, the biggest force. Based on that models, we took our results, and for example, we could calculate the deformations of the building. Here you see deformations in the x direction from the wind, or we could take the forces from the walls, and then based on that we reinforced through other programs the wall itself. So we don't use SIA to reinforce, at least not yet, and we take the forces and we reinforce with other softwares. Here you see the pi reactions. It's what I said before, it's almost 8,000. You see the forces in the middle. Another example here of analysis is from the transfer structure, where we put the truss in the model, and then we took the forces, and based on these forces, we were able to define and control the elements. Because before we put an element in SIA, we always try to make a quick calculation to see if it's okay to use that one, and then we confirm it with the analysis from the SIA. Here you see a lot of colors actually. You see the moments of in the floors which we used in order to reinforce it, and you see the difference. This is the 8th floor, so it's a standard floor plan with the balconies only at the side, and this is the floor plan with the balconies around. And here it's because in the I direction at the moment, and that's why you see on here bigger moment than this side. So every difference in the design is creating extra calculations, and we need to check every different scenario in order to make a safe construction. Another nice part of working in CoolTower for me is that I can actually see the CoolTower from my office. So this photo I made it today, it's for the current situation of the structure. It literally I can see from my desk, and as you can see now, it starts growing, and gonna have pretty soon we're gonna have the full tower, like this here you can see in the picture. That was it. Are there any questions?
Thank you, Alexandros. Somebody have a question? Well, at least I have a question. You were talking about the wings at the bottom, which are cantilevering, basically from the structure.
Yeah.
Do you feel like you used a large amount of concrete more compared to a conventional method where you just use piles to just support these parts in a normal way?
Not concrete, but steel, because we had to use extra steel to make this connection in between the walls. But in terms of concrete, we would be actually the same amount of they would be the same dimensions. It wouldn't be different, the dimensions of the elements. But in steel, we had to use extra because you cantilever, you have more tension in the construction. Was a good question.
I also have a question for the buildings next to the CoolTower. How much influence does it have during the construction, so that they might settle more?
Exactly. Yeah, because that's the reason that we kept this distance. So at the moment, there is no influence at the moment on the buildings. Otherwise, they would have now the main in the middle. The deformations are approximately 6 centimeters in the in the middle part, and on the side here are going to 3 centimeters. And so you can imagine, furthermore, there is no effect on the near buildings. And that's what was the reason of doing this kind of construction, because we are building in the middle of the Rotterdam, and everything is too close to each other. So we had to make a solution to make this construction.
I have another question. You showed at the start that your team was about 3 people. How is it to work on such a large project with such small team?
That's a good question, maybe. The thing is, when you're in the beginning of the design phase, you're working and you're actually also the project leader and the structure engineer and make calculations. And so it's working pretty efficient. During the construction phase, where you need more calculations and more production of engineering, more drawings, then there are also maybe there will be also an extra engineer, an extra modeler, but this depends per project. Normally we try to keep the teams as small as possible, because then also the information remains in the same team, and everybody knows the projects from themselves. So although I'm doing the same time also other projects, but as everybody in Rossum, we try to keep the teams the same also during the whole process of the project. It's a lot of work, I can admit, but it's also very, very interesting and very challenging.
Okay, thank you. I've got a question from the people sitting here. Which program do you use for your reinforcement?
Reinforcement, we use hand calculations or different Excel files we have, or we made ourselves, or we find from external parties, or we use Technosoft. Most of the times we use Technosoft for all the different, we calculate them per element.
Okay, thank you. I have a question again. Why do you use columns instead of walls? Is that to improve the flexibility of the structure?
You mean on the floor plan?
Yes.
So actually that's a good one. I didn't mention it. The vision of the architect was to create the most open facade possible. So he wanted to have a really light construction structure in the facade, and so that the views from there will be from floor to plafond free. And that's why we decided to use the columns and then focus the stability in the core. There were in this project there were different designs than in the past. There were also designs with walls in the beginning, but then we didn't go on because the vision, the wish of the architect changed. So here was we had to collaborate with the architect to realize his vision on this project. And that's what I also said in the beginning. We work a lot with the architect from the first moment, so that we can achieve the best result, and so we don't have any surprise in the end at the end of the project. And you see, we try to make the columns as thin as possible, and so that they are really open spaces, so for the users. That was the reason of the columns.
Okay, thank you. Does somebody else have a question? I've got the question. Why is the core made in situ and not in prefab or?
That was also decided from the contractor. Actually, the cores, the whole construction, how it's made, they use the construction system which is called Klinkist. Probably you know, everybody, I don't know how it's called in English. And then so the walls are climbing first. So that's why you saw in the photos, let me go back, you see in the photos here on top, these are the core walls. They are being first built, and then they follow the floors afterwards, after there. So there's a difference of 4 floors in between the walls and the floors, and they decided to use this system, but for the core walls and for the columns, in order to make it faster, they did the prefab elements. But in the core walls, it was just a decision of the contractor that he decided to use the system to build. So also there, we have to collaborate with the contractor to find an optimum solution, how to make it faster and more cost efficient. So we are always in between the project, trying to, especially in this kind of project where the structure is playing an important role, we have to collaborate with all the parties. I hope this answered the question.
Okay, thank you. Does somebody else have a question? I think we're out of questions here. And I'd like to thank you, Alexandros, for this great lecture. And have a good afternoon.
You're very welcome, everybody. Have a good day.